Good day, I'm Dr. T and welcome to my dining room table. So today I'd like to talk about chemistry in 3 dimensions. And the first one I want to talk to you about is the double bonds, because those actually come in 2 flavors. But to explain that, let me first look at some single bonds. So over here I have a model. This is 3-dimensional, it's made of wood, good old ball and stick configuration. And this is butane. Okay, so I got my butane, and with single bonds, you can rotate single bonds all day long. And they will rotate, and you will actually get scenarios where, okay, they're in this position, that's a little higher energy. You get a little bit better clearance if your hydrogens are kind of a little farther away from each other. So yay, everything's working pretty good. Just making sure the GoPro is happy. Now, so with this guy, this molecule and that molecule, they're literally the same molecule, and they will simply switch through and rotate all day long. No big deal. But if I switch this bond out for a double bond, there's going to be a little bit more of a story going on. So obviously, it's a double bond. I'm going to have to get rid of a couple of hydrogens. We call this an element of unsaturation. Whenever you can remove a couple of hydrogens, this is usually referred to as an element of unsaturation, and you can see that in the molecular formula, because in theory you could have more hydrogens than what you have, therefore it's unsaturated with hydrogens. And so when we talk about saturated fats, we're talking about ones without double bonds. When we're talking about unsaturated, we're talking about ones with double bonds. Okay, so I now have my double bond. Now, this one's a little bit unrealistic. In an actual double bond, if I was to look at this, I would have still the sigma bond between these two, but then I would have a second bond that would be arcing like my 2 springs are doing. That said, though, this does get the angles right, which is why this is done. You're going to get this kind of nice triangular shape. And additionally, you'll notice how this doesn't rotate. And that is the case for a double bond. So, for this double bond, that means that this molecule and let's see if I can make it. Okay, that was only mildly embarrassing. And that molecule are different molecules. They can't simply rotate and one become the other. So now we have isomers. Okay, now when distinguishing these, we of course need to describe them. There's 2 ways of doing so. Zaitsev and Itzi-Zaitsev, or the E and Z, or I should say Z and E, notation is one way of doing that. That's a pretty deep rabbit hole, so I'm not going to go into that. However, the other one that when you have hydrogens attached to your double bond is actually a little bit more valuable is called cis and trans. And this molecule we right now have is trans. If I look at the main chain and I look at it respective to the double bond, it's coming on one side of the double bond and then it transitions across to the other side. So we call this a trans double bond. If, however, this was like the previous molecule, and I learned my lesson on that last one, I'm moving the hydrogen this time. If it is in this configuration, making sure the GoPro's got a good photo, if it's in this configuration, then it's on the same side, and same is going to be cis. The difference between these guys, chemically, there is a little bit of a difference. It's not a ton, but there is enough to be important. Hydrogens are smaller than carbon groups. They provide less what we call steric hindrance. So if I have some atom coming in and attacking this side, it's going to be a lot easier to attack this side than that side. So this is going to affect how this is going to attach. Additionally, though, because the hydrogens are on this side, I've got this huge area where it can attack. It's not being blocked. But if this was in the trans configuration, now there's actually less of a window to attack. So for this reason, double bonds are typically more reactive if they're in their cis configuration than if they were in their trans configuration. And we actually see this with trans fats. Trans fats are artificial fats and they have a longer shelf life, which is why that they are liked by certain industries. They're disliked because they don't fit well within cells, and the normal cellular metabolism is really set up for cis fatty acids, or fats that contain cis double bonds, not trans, which leads to problems. Now, the other thing you'll notice when you have a cis fat, or I should say a cis double bond in general, not just fatty acids, is that you notice how there's this kind of kink going on? It creates this kind of horseshoe. This can't rotate, it can't go back in that kind of zigzag pattern. The trans typically gets a little bit of that zigzag back that, if you recall, you saw in the butane where there wasn't a double bond. This allows it to stack fairly nicely. So trans alkanes are going to have a little bit higher melting point than the cis alkenes will have. Okay, so with that said, that's a brief intro into trans versus cis, and I will talk about other three-dimensional arrangements of atoms in later videos. With that said, have a wonderful day.